So welcome back, everyone. We are ready to talk about MOSFETs again. So the subject of this lecture is understanding the IV characteristics of a ballistic MOSFET, where there's no scattering of electrons as they go from the source to the drain. They just move sort of like they were in vacuum, but with a different effective mass. Now, 10 or 20 years ago in my academic career, this would have been considered an academic problem. A ballistic MOSFET was not something that people really thought you could ever achieve. Today, we have transistors that operate almost at the ballistic limit. So this is a real practical problem. We need to understand the IV characteristics in the ballistic limit because we're quite close to them in modern technology. So let's begin with the linear regime. We have this simplified expression that we've developed from the more general Landauer expression for the low bias current. And we are going to assume ballistic transport now, so we'll simply make the transmission 1. That makes the integral easier to do. Okay, so when we do this, it's obvious that the current is going to be proportional to the drain to source voltage because the width of the Fermi window is proportional to the drain to source voltage. And we have an expression for the conductance of the channel, and we simply need to work that out. Now, I'm not going to go through the details of this derivation. I'm going to show you how it's done. Those of you that are interested in the details can see the fundamentals of nanotransistors and sections 13.3 and 15.4. Work through this in a little more detail. But the point is, we have an expression for the number of channels versus energy in 2 dimensions, and electrons flowing in the channel of a MOSFET are 2-dimensional electrons. We're going to assume ballistic transport. We're going to assume the Fermi function, but we will make the approximation that we're in the non-degenerate limit, so we can ignore the 1 in the denominator here. We also will try to relate this to the sheet carrier density, the number of electrons per square centimeter in the channel. We can work that out in 2D, and in the non-degenerate limit, it's given by this expression. And that effective density of states is related to the 2-dimensional density of states and the thermal energy KT. So with that input, we can work out that integral, and I'm simply going to show you the result. The result is that the channel conductance is proportional to width. That shouldn't surprise us. The wider the channel is, the more channels for current flow there are. It's like resistors in parallel. It's proportional to Q times the number of electrons per square centimeter. That's the charge in the inversion layer. And then this velocity divided by 2 kT over Q comes out from the analysis. Remember, that velocity I've called the unidirectional thermal velocity. We have an expression for that, and we're going to need to understand that in a little more detail, and we'll do that in just a minute. The inversion layer charge, if we're well above threshold, we can approximate that by minus Cox Vg minus Vt. And therefore, we can write the channel conductance as width times Cox Vg minus Vt times unidirectional thermal velocity divided by kT over Q. And we have derived the low bias linear region current in the ballistic limit. Okay, so we have our expression. Compared to the traditional expression, you can see that there's no length in this expression. So if we're in the ballistic limit, then it doesn't matter how long the channel is. If there's no scattering at all, if it's twice as long or 3 times as long, it won't affect the current in any way. So we expect to see a ballistic current that does not include an L in it. But note that the expression that we've derived here looks much different from the traditional expression, and we'll try to relate these two and make sense of them a little bit later. So a couple of questions. First of all, what is this unidirectional thermal velocity all about? And second, a second question we have is, this expression is so much different from the traditional expression. I've indicated earlier that when you fit IV characteristics with traditional models and just make small adjustments in the mobility and saturation velocity, it does a very good job even on nanoscale FETs. So how can a traditional model work so well when the proper model looks so different? So we'd like to discuss that as well. So first of all, about the thermal velocity. So let's look in the non-degenerate limit, which is where I've been doing the calculations just because it's easier to do them there. You can consult the fundamentals of nanotransistors lecture notes to see how it's done in the more general case. But in the non-degenerate limit, our Fermi function simplifies to an exponential. For parabolic bands, energy is bottom of the conduction band plus 1/2 mv squared. So our Fermi function is a factor times e to the minus 1/2 mv squared over kT. So that is a Gaussian distribution of velocities. If we were to plot that in the x direction, it would look like this. This is a thermal equilibrium distribution, so it's symmetrical around plus x and minus x. If I ask for what the average velocity is in any direction, it's 0, because for every positive velocity, I have the same number of negative velocities. So there's no average velocity at all. But if I were to ask a different question, what is the average velocity only of the electrons that are moving in the plus x direction? Well, then I can work out an answer. So first of all, what I would do is average over angle. All of them that have a plus x velocity component will average over angle in the xy plane. If you do that averaging in 2D, this is the answer that you will get. And then they're distributed in energy according to the Fermi function. They're not all at one energy, they're spread out over a range of energies. And then I would do a second averaging over that energy range, and I would weight each of the velocities times the density of states to get the number of electrons at that particular energy. So the first bracket indicates an average over angle at a specific energy. The second bracket indicates an average over energy of those angle average velocities. Now, if you do that, what you'll find is that the average value of the electrons with a positive velocity component, a positive x velocity component, is equal to square root of 2 kT over pi m. It's the average velocity only of the electrons with positive x velocities. Now, of course, the average velocity of electrons with negative x velocities is exactly the same. So the two velocities cancel each other out, and there is no overall average velocity in the x direction. But this is the physical interpretation of the unidirectional thermal velocity, which will occur over and over again in our subsequent discussions. Okay, now I want to move to the second question. How can this expression, this correct expression, how do we relate it to the more traditional expression, which for some reason seems to work at the nanoscale? The traditional expression looks so much different. But if you look at it carefully, we can do a little bit of algebra and show that we can make it look quite similar. So let's take a look at this term in parentheses, and let's multiply by L in that term in parentheses, and then let's divide by L. So now it's beginning to look like the traditional expression because we have a width divided by length out front. And we have an expression in the brackets that might look familiar to you. We've seen something like that before. In fact, we've seen something like that before when we worked out the mobility of a bulk semiconductor. If you look at the dimensions of that quantity, you can see that its dimensions are centimeters squared per volt second. So it has the dimensions of a mobility. We are talking about the ballistic case, so we'll call it a ballistic mobility. And if we compare that to the mobility we got for a large bulk sample in which there was a lot of scattering, the only difference is that instead of the mean free path for backscattering in the bulk case, we have the length of the channel. So it looks like the mobility with the mean free path replaced by the channel length. So we have these two components, ballistic mobility and diffusive mobility. Now, if I think about how do I make sense of this ballistic mobility, what does it mean? Let's think of our nano device here. Here's our energy band diagram. Under low drain bias, we have a slope in the channel and a finite electric field. We have some length of the channel. That's our little nano device between two contacts. The regions on either side are our contact 1 and our contact 2. If we look at our nano device, remember, contact 1 is a region of strong scattering. So the electrons scatter frequently. The channel is a region of no scattering. Contact 2 is another region of strong scattering that maintains thermodynamic equilibrium. So an electron that scatters frequently in the source then gets injected in the channel. It travels a length L, and then it scatters almost immediately when it enters the drain. So the average distance between scattering events in this nano device is the length of the channel. So it seems to make physical sense to replace the mean free path for backscattering in the bulk with the length of the channel. So there's a sound physical interpretation to what this ballistic mobility means. Frequently, people's first reaction when you talk about ballistic mobility is, that's nonsense. Mobility is all about what happens when you have a lot of scattering. Well, even in the ballistic event case, you have a lot of scattering in the two contacts, just not in the device itself. So here's our linear region summary. We can actually write the ballistic current just as we wrote the traditional current. It's just that we have to replace the actual scattering limited mobility by this quantity we call the ballistic mobility, which has a nice, clear physical interpretation. Okay. All right. So we know how to treat the ballistic limit. We use the ballistic mobility. We know how to treat the diffusive limit. We use the diffusive mobility. Obviously, we want to treat the in-between region, which is where most transistors operate, and we'll discuss that in the next lecture. All right, now let's shift our attention to the high drain bias saturation region and see if we can understand how we replace the traditional expression, which includes this scattering limited saturation velocity, how we replace that with the appropriate quantity in the ballistic limit. We've seen that under high drain bias, F2 is 0, so F1 minus F2 is just F1. We simply have to work out this integral and we'll find what the answer is. We're going to focus, now you have to ask, well, where in the channel are we doing this? Under low bias, it didn't really matter because the drain bias was so small, things were essentially constant everywhere along the channel. Under high drain bias, things are varying rapidly within the channel. We are going to focus on the top of the energy barrier, the so-called virtual source. We're going to do that because that's a region where we don't have any electric field in the lateral direction. We only have an electric field in the direction normal to the channel. Our 1D MOS electrostatics, where we deduced that charge is minus Cox Vg minus Vt, should hold. If it holds anywhere, this is the place it's going to hold. So we know the charge at that point. It seems to be a good place to focus on evaluating the current. Things get very complicated down the channel where we have very high electric fields. So if I look at the electron density at the virtual source, let's talk about that for just a minute. If I look at the electron density at the virtual source and ask, how are these states populated, these states with positive velocity? In the ballistic limit, there is only one way that they could have been populated. Electrons flow in from the contact 1 and occupy those states, and the probability that those states will be occupied will be given by the Fermi level of contact 1, because that's where they're coming from. These electrons are in thermal equilibrium with contact 1. There will be no possibility of electrons coming in from the negative velocities, electrons coming in from contact 2, because the voltage is so large that F2 is close to 0. So we have electrons that have positive velocity, I'm calling them NS+, but we have no electrons with negative velocity, I'm calling them NS-. The total electron charge is this capital Q sub n that is determined by MOS electrostatics. We know what that is. The gate voltage tells us what that is. And it's the sum of the positive velocity electrons and the negative velocity electrons. Under high drain bias, we have only positive velocity electrons. So if we put this together, we know that the charge at the virtual source, we know what it is, Cox Vg minus Vt, and we know that it is only due to positive velocity electrons. Okay, so now we can go back to working out this integral. We know the number of channels versus energy for two-dimensional electrons. We're ballistic, so transmission is equal to 1. We're going to assume non-degenerate statistics, so the Fermi function simplifies to an exponential. We're going to see that this unidirectional thermal velocity is involved when we collect up constants after we do this integral. And we also know that the electron density now is not given by effective density of states times E to the Fermi level minus conduction band over KT. It's given by 1/2 of that, because we only have half of the states can be occupied, half of the states that have positive x-directed velocities. So putting that all together, going through the algebra, we can work out that integral and we can see what happens. This is what happens, remarkably simple. The saturation current is proportional to the width of the MOSFET, to the charge in the inversion layer, Q times the electron sheet density, times the unidirectional thermal velocity. Okay. The charge on the electrons is just, if we're doing simple MOS electrostatics, assuming that we're well above the threshold voltage, it's minus C inversion times Vg minus Vt. So we have derived a very simple expression for the saturation current. So if we look at this expression, we have a simple expression. The only thing that has happened, it looks very similar to the traditional expression. We have simply replaced the scattering limited velocity by the thermal equilibrium unidirectional velocity. So we'll have to talk a little bit about why that makes sense, but it's remarkably simple and remarkably close to the traditional expression. We just have to reinterpret that velocity. It's not the scattering limited velocity. All right, so to conclude, we really would like to describe the entire IV characteristic. So let me quickly explain how we go through that. That means we have to assume F1 minus F2 across the entire range of voltages from small to large. There are really two currents here. There is a contribution of electrons flowing from the source to the drain, and there's a contribution of electrons flowing from the drain to the source, and we have to subtract the two to get the net current. Now we can write each one of them from source to the drain. It's minus W times the charge with positive velocities times the thermal velocity that they're injected at from the contact. For the current from the drain to the source, it's minus W times the charge due to electrons with negative velocity, and they're also injected at the unidirectional thermal velocity from the second contact. We put the two together, we just subtract the two. If I subtract the two and pull Qn plus out front, I get this expression. So here's where we are. We have an expression for the charge, for the net current in terms of these charges. We'd like to express it in terms that are more clearly related to what's happening at the terminals. So remember that under general conditions, the total charge is the sum of the charge of electrons with positive x velocities and the electrons with negative x velocities. So we can pull out a Qn plus and write it this way. We can then relate Qn plus to the total charge, which we know from MOS electrostatics with this expression. We can put this expression into our expression for current and replace the Qn plus, which we don't know in general, now with Qn total, which we do know. And now we'll realize without working out Qn minus and Qn plus, we know that the only differences between those two quantities are the fact that their Fermi levels are in different locations. Charge depends exponentially on the location of the Fermi level with respect to the bottom of the conduction band in the non-degenerate limit. And the only reason that those two Fermi levels are different is because of the drain to source voltage, which puts them in different places. So the ratio of Qn minus over Qn plus is just e to the drain to source voltage over kT. Put that all together, and now we have our full range expression for the IV characteristic from the linear range to the saturation regime. And it's a remarkably simple expression in the ballistic limit. So here's what we have. We have a general expression that gives us the entire IV characteristic. If we were to expand these exponentials for small argument with small drain to source voltage, we would get the expression for the linear region current that we derived first. If we were to take the limit where the drain to source voltage is large, we get the expression for the saturation current that we described, that we derived independently in the second part of this lecture. So we have a full IV expression that we'll make use of in the next lecture. So we can now go from small to large drain voltages. We would like also to go from subthreshold to above threshold, and that means we can't use this expression Cox Vg minus Vt or C inversion Vg minus Vt, which only applies well above threshold, but that's easy to fix. We can simply replace that by the total inversion layer charge either below threshold or above threshold. And we saw in Unit 3 on electrostatics that we have an expression that we developed that takes us smoothly from below threshold to above threshold, and we'll simply make use of that expression. So we can easily modify our expressions. We just use the total charge here. It could be subthreshold charge, could be above threshold charge. Now we have an expression that is going to describe the linear region, the saturated region, and it's going to describe the IV characteristics, whether we are in linear, in saturation, or in between, whether we are in subthreshold, in strong inversion, or in between. So we have a very comprehensive ballistic IV characteristic model. So what we've learned is that the result is remarkably easy to remember and to understand physically. We simply take the traditional expression and we replace the diffusive mobility, the traditional mobility, by the ballistic mobility, and we know how to interpret that. We take the traditional expression for the saturation current and we replace the saturation velocity due to scattering in a high electric field, and we replace it by the thermal equilibrium unidirectional thermal velocity. And we'll discuss in the next lecture why that makes physical sense. But we have a very simple way to extend our traditional model all the way to the ballistic limit. So in the next lecture, what we would like to do now is just shift our attention for a moment to the velocity. Current is charge times velocity. And let's look in a little more detail at how the average velocity at the virtual source varies as we increase the drain voltage from large to small. We'd also like to understand how it varies as we increase the gate voltage from large to small. This is going to give us some more insight into the operation of the transistor itself. That's what we'll be discussing in the next lecture.